Hey everybody, we're live and in stereo, starting off 10 minutes late, always because you all show up late to the class. Yes. So, without further ado, let's just start off with the idea of equilibrium constant. I'll give you guys a quick recap of what we've done up until now. We've learned what equilibrium constant is. It's basically a ratio of products to reactants, and we use, multiple equilibrium constants. And the equilibrium constant that we've learned up until now is the Kc equilibrium constant, which has to deal with concentrations at equilibrium, right? So at the start of this entire chapter, the examiner was giving us concentrations at equilibrium, and we were just making Kc expressions. For example, A plus B gives me C, let's suppose. So what would the Kc expression look like? Let's suppose this is 2 moles of C and this is 1 and this is, let's suppose, 3. So how would it look like? It would look like this: C's concentration raised to the power of its coefficient, right, raised to its coefficient. A's concentration at equilibrium raised to its coefficient. B's concentration at equilibrium raised to its coefficient, which is 1. We don't normally write 1, right? That's the Kc expression. We've learned how to write Kc expressions. Number 1, we've learned how to write the units for every equilibrium constant Kc expression, right? You know how to write the units now. This is m square and this is m to the power 4, so m minus 2, and then you replace m with mole per dm cube and whole to the power minus 2. We've done all of this. So we've learned how to write units. We have also learned relationships which would help us in our MCQs, relationships, the reverse relation. If you double the coefficients, what happens to the Kc? If you half the coefficients, it's basically under root. If you triple it, it's basically triple the coefficients of the equation. It's basically a cubic effect, to the Kc. And, if you talk about the reverse reactions Kc, it's inverse of that, it's flip of that. And we talked about all of those good relationships. Then the examiner said, hey, before I was giving you concentrations at equilibrium, now I won't. Figure it out on your own. I'll just give you the initial moles reacting. And for that, we learned the idea of ice table. So he just gave us initial moles, and through the initial moles, we looked at the change and we ended up at moles at equilibrium. And then we divided it by the volume, which would give me concentration at equilibrium. And these moles at equilibrium are equal to the concentration at equilibrium if Kc has no units. If Kc has no units, then obviously all the V's, all the volumes cancel out. So moles at equilibrium equals concentration at equilibrium. But then we also figured out that the examiner sometimes made us do reverse working. He gave us Kc, which is, let's suppose, 4.0, and he gave us, like, for example, the initial moles, but he wanted what? He wanted the final moles, or the moles at equilibrium. And so through that, we actually figured out, through Kc's and some mathematical techniques, we actually, and the same ice tables, using the same ice tables, we actually figured this out. And fun fact, this is actually the most important use of Kc, which is reverse working. In the world, in your day-to-day life experiments, scientific experiments, that Kc's, the concentrations, do not change if the experiment is carried out at the same temperature. The Kc, not the concentration, the concentration constant, the equilibrium constant for concentration, this does not change for the same temperature. It will always remain 4.0, 4.0, 4.0, no matter what the final moles are. No matter what moles are at equilibrium, this doesn't change. And in reality, your Kc values. You want moles at equilibrium or concentration at equilibrium. And we've done all of that good stuff. Now, today what we want to do is we want to learn the second aspect of equilibria, which is we've learned Kc is actually what? It's called equilibrium constant for concentration, right? We talk about concentration and all of that good stuff. But today what we want to do is we want to learn something known as gaseous equilibria. Gaseous equilibria. Sir, what in the hell is gaseous equilibria? Can you actually help us out? I'll tell you. Before I actually tell you and actually start teaching you the formulas for gaseous equilibria and what it actually is, I want to derive it for you all, right? So it sits in your brain. For example, I'll tell you. You all must be knowing that pressure is directly proportional to concentration. Pressure is directly proportional to concentration. Pressure of a gas, obviously. Pressure of a gas is directly proportional to concentration. You all must be knowing this. Sir, how can you expect us to know all of this? We don't know this. We don't know this stuff. But please tell us, how is pressure of gas directly equal to concentration or directly proportional to concentration? Please help us out. I'll help you. See, it's very simple. What's concentration? How do you calculate concentration? N equals CV, right? N equals CV. That's how you figured out concentration, right? And this is the relationship of concentration with moles. If the volume for gases is constant, if the volume is constant, or if the volume is constant, I know that moles is directly proportional to concentration, isn't it? So the higher concentration you're going to have, the more the moles you're going to have, right? If volume is constant, you could say concentration is directly proportional to moles, right? So the higher the concentration at the same volume, you know that the moles are increasing. The higher the moles, right? And the more moles you have, does that also mean the more molecules I'm going to have? The more moles I have, does that mean the more molecules I'm going to have? Yes. More moles equals more molecules. And more molecules means more collisions with the walls of the container. And more collisions with the walls of the container, or higher frequency of collisions, bombardment means what? Higher pressure. And so here you go. I've connected concentration to pressure. That pressure of a gas is directly proportional to its concentration. Because the more concentration you have, the more moles you're going to have. The more moles you have, the more molecules you have. The more molecules you have, the more collisions you have. The more collisions you have, the higher the pressure of this gas. So pressure is in fact directly proportional to concentration. And it's basic. It's like pretty simple. You just needed to connect these two, right? And this is what we need to know. You don't need to know the derivation for it. It's just there to sit in your brains. But pressure of a gas is directly proportional to concentration. And this is what we use to our advantage. What we do is we say, hey, if in my reversible reaction all components are gases, if all components in a reversible reactions are gases, we can come up with a new equilibrium constant, and we call that equilibrium constant Kp. This Kp, this is the equilibrium constant for pressures. This only works, please understand that this only works if you have gases. If you have gases in your reactants and products, this only works, right? And the idea of Kp revolves around partial pressure. And we've discussed what partial pressure is in States of Matter chapter. And those who have not taken States of Matter, I'll just quickly revise it for you. But please, you need to go over it. I've discussed partial pressure in States of Matter, right? Now, what do you mean that this equilibrium constant Kp is in terms of partial pressure of a gas? Sir, what is partial pressure of a gas? Please, I've already taught it, but I'll just quickly recap it. I'll quickly recap it through an example. See, if you have a container right here, and for example's sake, I'll say this container has inside this container, there's a pressure of 1 atmosphere, right? And you have about 80% nitrogen and you have about 20% oxygen, right? And this container has an overall pressure of 1 atmosphere and it has 80% nitrogen, 20% oxygen. 80% nitrogen means what? That if you have 10 molecules in total, if you have 10 molecules, 8 of those molecules are going to be molecules of nitrogen, 3, 4, 5, 6, 7, 8. 8 are going to be molecules of nitrogen and 2 are going to be molecules of oxygen, right? And so this partial pressure, this is actually Dalton's law of partial pressure, right? Dalton's law of partial pressure, which I've already taught you guys, and it's going to be used here now, says that, hey, if you have 80% nitrogen and 20% oxygen, right? These two pressures, nitrogen will exert a pressure and oxygen will exert a pressure. And the total pressure in this entire container is the sum of these individual pressures, which we call partial pressures. So the total pressure is equal to the partial pressure of nitrogen plus the partial pressure of oxygen. Right? That's the idea. I've discussed it in more detail in the last States of Matter chapter, but I assume that you guys not all of you have studied from me. Therefore, I'm just quickly recapping it, right? So 1 atmosphere pressure, if that's the entire pressure of this container, inside this container, and you have 80% nitrogen and 20% oxygen, this entire pressure is going to be made up of 80% of nitrogen, right? Is going to be made up of 80% nitrogen contributing to this and 20% oxygen contributing to this, right? So this total 1 atmosphere pressure is because of the partial pressure of nitrogen and the partial pressure of oxygen. The partial pressure is basically the pressure that nitrogen would exert if it alone were to exist in this entire container. The pressure that oxygen would exert if it alone were to exist in this entire container. Right? And what is that? Well, for nitrogen it's pretty simple, and for oxygen it's also simple, right? What is that? How do you calculate partial pressures? Well, 80%, you have nitrogen, right? 80% is nitrogen, right? 80 means what? 80% means what? 80 divided by 100. So out of 100 molecules, 80 would be nitrogen. And so how much pressure would nitrogen be contributing? Well, times it by 1, times it by the total pressure. So nitrogen is effectively contributing 0.8 atmospheres. Right? And if you check oxygen out, it's 20%, 20 over 100 into 1 atmosphere, or you could just say 20% into 1 atmosphere. What does that give me? 0.2 atmospheres. So the total pressure inside this container is the sum of these partial pressures, the partial pressure of nitrogen and the partial pressure of oxygen, right? Yes, sir. And this is literally a ratio. That's it. That's all it is. How do you calculate partial pressures? You take the ratio, which is the total molecules of nitrogen present divided by the total molecules of gas present. So the total molecules, if it is 80%, that means 80 out of 100 is nitrogen. 20% means 20 out of 100 is oxygen. And then that's how you calculate the partial pressures, don't you? So if I were to say 1 atmosphere is equal to, how is this 1 atmosphere calculated? The total pressure, how is the total pressure calculated? The total pressure is calculated by taking the individual pressures, the partial pressure of nitrogen and the partial pressure of oxygen. See, that equals to 1 atmosphere right here. That's a piece of cake. And this stuff right here, this can be in percentages, it can be in volumes, it can be in ratios, it can be in moles. Normally, it's in the form of moles, right? For example, I'll give you another example. Let's suppose you have 2 moles of nitrogen and let's suppose 1 mole of oxygen inside a container. And the total pressure of that container is 1 atmosphere, right? What's the partial pressure of nitrogen? Well, you know that in this entire container, you actually have 3 moles. 3 moles in total, right? So what's the partial pressure of nitrogen? Sir, the moles of nitrogen present divided by the total number of moles multiplied by the total pressure. What does that give me? Whatever that gives me, that's the partial pressure of nitrogen. 1 divided by 1 mole of oxygen is there, divided by the total moles, which is what? 3. Times it by the total pressure, which is 1 atmosphere. So this will give you partial pressures. And I've discussed partial pressures in a lot more detail in States of Matter chapter. That's why I'm just quickly going over it. Right? Now, in this particular chapter, we're going to use partial pressures to calculate Kp. Right? And please understand, for gases, Kp and Kc are literally equal. And I've proven it right here. Because moles are directly proportional to concentration. So if concentration increases, moles also increase. And moles increase, molecules increase, more collisions. More collisions mean more pressure, right? So if whatever value you have for Kc is going to be the same for Kp, provided they're all gases. Kp only works for gases because it works on the idea of partial pressures. How does it work on the idea of partial pressure? We're going to look into that in a moment, right? And this part right here is also called mole fraction, remember? And you used to represent it like this in States of Matter chapter. Yeah? Mole fraction. Right? That's the idea. And see, this can be in not just in moles, this can also be in the form of volume, that nitrogen is 48 dm cube and oxygen is, let's suppose, 24 dm cube. So what is the partial, if the total pressure is 1 atmosphere, what's the partial pressure of nitrogen? Well, nitrogen is 48 dm cube. Divided by what? Divided by the total volume of this inside this entire container, which is 48 plus 24, 72, and into 1 atmosphere. Right? Similarly, and the answer is going to be the same. Similarly, for oxygen, it's 24 dm³ divided by the total volume multiplied by the total pressure. That's it. That's how you calculate it. We've done it in a lot more detail in states of matter again. Right? Now, normally in this particular chapter, we deal with moles, right? We deal with moles. So you can assume that whatever data you are given, just convert it into moles, and this idea would be used right here. But it can be in any form, shape, whatever. Right? Okay. Now, we know that for gases, we can actually now use the idea of Kp instead of Kc. Right? And we know for gases, Kp and Kc are equal. That's one takeaway up until now. The second takeaway is that we know that this Kp, how is it calculated? It's calculated using the idea of partial pressures. And we already know how to calculate partial pressures. I just recapped it a little, in a very quick manner right here. Just recapped how to calculate partial pressures. It's the moles of that substance divided by the total moles into the total pressure. That's how you calculate the partial pressure of nitrogen oxygen, right? And we know what it is in very much detail. Right? Now, for Kc, if I give you guys gases, for example, I give you guys an equation: A gas plus 2B gas, and it's a reversible reaction, and gives me C gas plus 4D gas. One idea is to use Kc, right? In order to figure out where the equilibrium lies, I can use Kc, which is what? C raised to the power its coefficients, D to the power of its coefficient, which is 4, A to the power of its coefficient, which is 1, and B to the power of its coefficient, which is 2, right? And these are concentrations at equilibrium. Please, we know that, right? And if we are not given this, we figure it out through ice tables, don't we? Now, because these are gases, I can also use the idea of Kp here. They're all gases. So I can use the idea of Kp. Sir, if you can use the idea of Kp, why are you doing this? Why just not stick to Kc? Because in the exam, he'll not give you information about concentrations. Then what? So you need to know both, right? So for gases, you can use the idea of Kp. And the Kc value and the Kp value are going to be the same. Literally, they're going to be the same. And I've proven why they'll be the same. They'll be the same because pressure is directly proportional to pressure of a gas is directly proportional to concentration. You won't get this anywhere else. Nobody's going to tell you this stuff, right? So how do you calculate Kp? Now, instead of using these square brackets, remember these square brackets represent what? These square brackets represent concentrations at equilibrium in the form of mole per dm³. This is what square brackets mean. So we can't use square brackets, can we? We can't use square brackets. I could say C to the power of 3. I could say D to the power of 4, I could say D to the power of 4. And A to the power of 1 and B to the power of 2, right? B squared. I can say this, but I can't use brackets. Then what do we do? Sir, the nomenclature for it is that you put a slanted P like this. This P represents that, hey, now you're talking in terms of partial pressures. So it's partial pressure of C into partial pressure of D into partial pressure of A. So divide by partial pressure of A into partial pressure of B. So instead of using these square brackets, we use this slanted P, right? This slanted P. And you could also, in some books, they also write it like this: P D to the power of 4, P C to the power of 3 divided by P A, and they put like these parentheses, P B squared, like this. So it's your choice. You want to do it like this, or you want to put slanted P's and put them in parentheses, that's it. But you can't use square brackets. See, these are nomenclatures that you need to stick to. Why did they do this? To differentiate between these two. My question to you guys is very simple. This partial pressure, is it the initial partial pressure or is it the partial pressure at equilibrium? This is my question. Sir, what would be the units for it? The units can be in pascals, or you could also write ATM, atmospheres. It's up to you. But for this, you can calculate the units, right? So see, it's 3 and 4. So let's call it ATM. So ATM to the power of 7 divided by ATM to the power of 3 because this is 1 plus 2, that's 3, right? 3 cuts out, here you're left with 4, ATM 4 to the power, this is the unit. Or you could say pascals to the power of 4. My question to you guys is this, when you were talking about concentration, this was the concentration at equilibrium. Is the partial pressure, does it need to be at equilibrium or no? We don't mix anything, Mahat. Hanji, please help me out, everybody. Yeah. So it must be at equilibrium. You're all right. It must be at equilibrium. So the partial pressures that you want to calculate, the Kp that you want to calculate, this is only going to be calculated if these partial pressures are at equilibrium. And in order to reach the partial pressures at equilibrium, how do you calculate partial pressures? Fun fact, how do you calculate partial pressures? Sir, you take the moles divided by the total moles and multiplied by the total pressure, right? This is how you calculate partial pressures. So if you were to calculate the partial pressures at equilibrium, how would you do that? You would need what? You would need the moles at equilibrium, wouldn't you? The moles at equilibrium. And then you would need the moles at equilibrium, and you would need the total moles at equilibrium, wouldn't you? And you would need the pressure, the total pressure at equilibrium, or the total pressure, right? So I'm not going to use the initial moles, I need the moles at equilibrium. See, 2 divided by the total moles, and these would be the moles at equilibrium into the total pressure. How do we end up with the moles at equilibrium? How do we end up with equilibrium moles? How do we end up, if we are not given equilibrium moles, how do we end up with them? If we are not given moles at equilibrium, how do we end up with them? Right? We end up with them by using our ice tables. So it's literally ditto. It's the same, no difference whatsoever. Instead of concentration at equilibrium, you're using pressures, partial pressures at equilibrium. And for you to calculate partial pressures, you need the moles at equilibrium divided by the total moles at equilibrium into the total pressure. That's what we need, right? And in order to get the moles at equilibrium, you need ice tables, don't you? Now, before I make you guys do that advanced things, let me just give you guys the partial pressures at equilibrium, or the moles at equilibrium. Chalo, I'll give you the moles at equilibrium. Moles of nitrogen, for example, at equilibrium is 2.15. Moles of hydrogen at equilibrium is 6.75. Moles of NH3 at equilibrium is let's suppose 1.41, right? These are the moles. Now, what are the total moles at equilibrium? Total moles at equilibrium. Somebody help me out. What are the total moles at equilibrium? Sabar kariye Hamza, you'll understand ice tables again, don't worry. We're going to do more and more practice for it. What are the total moles? Can you guys sum this up, please? I think it's a grade 2 question that I'm asking. What are the total moles? And question is, the total pressure is 10 atmospheres. Total moles are how many? 10.31. Okay, I'll trust you. 10.31 are the total moles, right? Now, listen. I want to calculate the Kp or the Kc, please. If I were to calculate Kc, I'm not given any concentration data. Am I? Am I given concentration data? I'm not. I'm given what? I'm given the moles at equilibrium, the moles at equilibrium, the moles at equilibrium. I'm not given the concentration at equilibrium. I'm not given concentration at equilibrium. And what's the equation for it? Nitrogen plus hydrogen gives me what? 2NH3, right? And so I can't even, you guys can say sir, in some other questions, concentration, in some other questions, volume wasn't given at equilibrium. Here it's must. Here it's must because see, the units for Kc don't cancel out and I'm not given that data. So I can't figure out concentration at equilibrium, can I? Right? The moles at equilibrium are not equal to concentration at equilibrium because, why? Because these Kc values, these coefficients, they don't cancel out. Kc has units, right? This is NH3. If you want to write the Kc equation for it, what would it look like? Kc is equal to concentration of NH3 raised to the power 2 divided by concentration of nitrogen. And then It's concentration of hydrogen. You don't have concentrations. And you might say, hey sir, but can we not call concentrations X? You can, but you won't be able to solve it because the units don't cancel out. The V's don't cancel out with each other, remember? So we are now majboor. We are, what's majboor called in English? We are now compelled. We are now compelled to do it through Kp. Right? Because Kp will be equal to Kc, but we have to do it through Kp. How do we do it through Kp? We say, hey, partial pressure of NH3 squared divided by partial pressure of nitrogen at equilibrium into partial pressure of hydrogen at equilibrium. Cube, right? Yeah, that's it. That's the idea. Now, the idea is that you need to first calculate the partial pressure of ammonia, don't you? The partial pressure of ammonia. How do you calculate the partial pressure of ammonia? Sir, you're given the moles of ammonia at equilibrium. You're given the total moles, sir, and you have the total pressure. So the moles of ammonia, 1.41, divided by the total moles, 10.31, into pressure, which is 10. This is the partial pressure of ammonia. Right here, somebody calculate it, please. Then hydrogen ka partial pressure. How do you calculate hydrogen's partial pressure? So the moles of hydrogen at equilibrium divided by the total moles at equilibrium multiplied by the total pressure. That's the partial pressure of hydrogen. What's the partial pressure of nitrogen? Sir, the moles of nitrogen divided by the total moles into the total pressure. And please, these are all at equilibrium, at equilibrium, at equilibrium. Done. What do you get? Somebody help me out. You get 1.37. Okay, 1.37. I'm just going to round it out to 2 dp. 1.37. What do you get here for nitrogen? For hydrogen, sorry. 6.55. Okay, 6.55. What do you get here? 2.08. 2.08. Thank you. So these are now the partial pressures. And that's it. Once I have partial pressures, what do? Square it for ammonia. So 1.37 squared divided by partial pressure of nitrogen is 2.08. Partial pressure of hydrogen, which is what? 6.55. So 6.55 to cubit. What do you get? 3.21 into 10 raised to the power minus 3. What's going to be the units for it? See, this is ATM squared and this is ATM to the power of 4. Right? So ATM minus 2. Done? Yeah, pretty basic, pretty simple. Right? Easy. So it's the same, no change whatsoever. No change whatsoever. You, instead of having concentration at equilibrium, the only change is now you need partial pressures at equilibrium. And for partial pressures, for you to calculate partial pressures, what do you need to do? You need to have the moles at equilibrium and the total moles at equilibrium and the pressure. So the moles at equilibrium for NH3 divided by the total moles, the moles of hydrogen at equilibrium divided by the total moles at equilibrium, the total moles of this divided by the total moles. Because see, if it's at equilibrium, only then would you know what pressure it's exerting at equilibrium. So you need to make sure that these are the moles at equilibrium, don't you? Now, again, Cambridge examiner is not a very gracious person. He's going to say, okay, in this case, just like when I was teaching you KC, the Cambridge examiner is saying, just like when I was teaching you KC, I gave you guys the moles at equilibrium or the concentration at equilibrium, and you actually plugged it in the equation for yourself. But hey, I'm not that good. Figure it out on your own. Figure out the moles at equilibrium on your own. Okay, I'm going to say, okay, moles at equilibrium, figure it out. I'm going to say, okay, Cambridge examiner, at least give me some data. Give me some data. The examiner says, okay, I'll give you some data. I said, okay, please do. The data the examiner is going to give me is, as he's going to say, hey, the reaction is as follows. NO plus O2. These are all gases. Right? And the moment you see gases, you could directly, it should come in your brain that I could also use Kp for this. Kp would be equal to Kc. Right? So these are all gases. Now the examiner, what he's going to do is, he's going to say, initially, I mixed about like 0.357 moles of nitrogen monoxide and 0.229 moles of I suppose oxygen. Right? I basically mixed these two moles together, right? And the moles at equilibrium for NO2 are equal to, let's suppose, 0.291. And he says find Kp. Find Kp if the total pressure is 100 kilopascals. Done. Find Kp if the total pressure is 100 kilopascals. It can also be in kilopascals. Units don't really matter. You can calculate in kilopascals, you can calculate in atmospheres, it's up to you. How do we do this? See, first of all, always remember the first step. Wherever you go in life, always remember to write the basic idea first, which is what? I'm not given any data about concentrations, but I'm given data about pressures. And I can therefore use Kp. And always, the first step should always be to write the expression for yourself. So Kp's expression should look like what? The partial pressure of NO2, squared, right? Divided by the partial pressure of oxygen to the power of 1, right? And then, I'm just going to put brackets around it. Nobody cares. Partial pressure of NO squared. Done. Partial pressure of NO squared. Partial pressure of NO2 squared. Divided by this stuff right here. Done. Now, this is the first thing that I wrote for myself. And so from this, I will first derive the idea that, hey, I need partial pressures at equilibrium. He's not given me moles at equilibrium. Has he? He hasn't. I have to figure it out on my own. Okay, let's try to figure it out. Let's use ice table like we were using before. It's literally no change. Remember, it's no change from Kc. It's the same idea, same everything. So, what am I going to do? Same old ice tables. In the entire world, these ice tables are followed. So I'm going to put NO, 2NO plus O2 gives me 2NO2. Right? Initially, how many moles did you have of NO? You had 0.357 moles. 0.357 moles of NO. You had 0.229 moles. 0.229 moles of O2, and you had 0 moles of NO2. Why? Because it's products. Products initially are 0. And now I'm saying at equilibrium, the moles of NO2 that you have at equilibrium are 0.291. So these are 0.291. And since this is product, this must have formed. So I'm going to put a plus sign to it. That's the change. And from this change, now I can use this middle equation to go into the changes in nitrogen monoxide and oxygen. How? Well, it's 2:2. So for nitrogen dioxide and nitrogen monoxide, whatever change you have for nitrogen dioxide, that change would be there for nitrogen monoxide. But since it's a reactant, it'll be used up. Therefore, I'm representing it with a negative sign. Done. And for oxygen, this is 2:1. So it's going to be half. Right? Or you could say, hey, this is 2:1. It's going to be half. Whichever one you use doesn't really make a difference. So half this, please, for me. Please half this. What do you get? When you half this, what do you get? 0.146. So minus 0.146. Why minus? Because they are reactants. They're going to be used up. Can you tell me the moles at equilibrium? Shabash. Moles at equilibrium. Please help me out. 0.066. Okay. What do you get here? 0.083. Thank you. Okay. These are the moles at equilibrium. And you also, if you sum them up, you'll get the total moles at equilibrium. Well, how many total moles are there at equilibrium? The total moles at equilibrium are 0.44. These are the total moles at equilibrium. And you're good to go. Because now you could calculate the partial pressures at equilibrium. How do you calculate the partial pressure of NH3? How do you calculate the partial pressure of NO2 at equilibrium, partial pressure of O2 at equilibrium, partial pressure of NO at equilibrium? How do you do that? Sir, it's a piece of cake now, because I have the moles at equilibrium. For NO2, I have the moles. It's 0.291. These are the moles divided by the total moles into the total pressure, which is 100 kilopascals. Done. Similarly here, oxygen is 0.083. That's the moles of oxygen divided by the total moles, which is 0.44 multiplied by 100. Again, right here, 0.066 divided by the total moles multiplied by 100 kilopascals. What do you get, sir? Partial pressure. And then you just plug it in your expression. Kp equals, can you guys tell me the partial pressure of NO2? Help me out. Sir, how you find moles? I've discussed it. Did you attend all the previous classes? Have you attended all the previous classes? If you haven't, you need to attend that. Yes, Hamza, you use a negative sign for reactance as it is. No matter how you find it, reactants are used up. So the change is going to be negative. This would decrease. No matter if you calculate it from here, wherever you do, the negative and positive has to do with change. Products already are zero. So the change would be positive. They would form at the end. So this would always be positive for products and always be negative for reactants. Right? Hope it makes sense. Yes, pressure also does not make a difference on Kc. You're right. And Kp. Right. It's only temperature which changes these equilibrium constants. Nothing else. They remain the same for a particular temperature. Okay, what do you get, sir? This is 15 kilopascals. Okay. What is NO2 के लिए? It's 66.1 kilopascals. इसके लिए it's 18.9 kilopascals. I hope you've done the calculation correct. Now what's the Kp for it? Kp is equal to, I'll just copy the same equation, PNO2 squared O2 and NO, PNO2 squared O2 and NO. It's a piece of cake. It's a piece of cake. NO2 squared, you have the partial pressure of NO2, which is what? 66.1 kilopascals. So 66.1 squared divided by oxygen is what? 18.9 multiplied by NO is what? 15. Figure it out. What do you get? 15 ka squared, obviously. Yeah. What would be the units for it? See, this is kilopascal squared and this is kilopascal cube. So it should be inverse. Kilopascals minus 1. Right? Because it's going to be 1 over kilopascals which will be left behind. What's the answer for it? So 1.03 kilopascals. That's the Kc for it, the Kp for it. And the Kc would have the same magnitude, which would be 1.03. Piece of cake, huh? Sir, when we find reactants mole from products or mole, I think I answered this question, Hamza. Done? Kilopascals, but it's going to be kilopascals negative. Why, sir? Why is this the unit? Please see. This is kilopascal squared here. Kilopascal squared divided by kilopascal cube. Sir, why are you cubing it? Because see, this is 1. 1 plus 2 is 3. So kilopascal squared and cube, this is 1 left. So it's 1 over kPa. And I can't help this, guys. If you don't know that 1 over Kp, if you want to take this upwards, it'll be Kpa minus 1. If you don't know this, I just can't help it. Kiddo, I can't help this. This is grade 4 math. Just now rote learned this. I don't know. I'm against rote learning, but you need to fix your basics. If this goes up, then this Pascal is going to have a negative sign. It'll still be kilo, but this Pascal is minus 1. All right. Done? It's the same idea. Chalo, I'll give you one more question. Do it on your own now. Do this question on your own and you'll be good to go. I'm going to give you the same reaction. 2NO plus O2 gas and gives me 2NO gas, right? And the question is, if I have about 10.7 grams of NO and I have about 7.33 grams of O2 that I'm reacting, and they are all mixed at the same temperature, let's suppose 400 Kelvin, nobody cares, but same temperature, and the total pressure at the end, total pressure equals 100 kilopascals, and at equilibrium, the mass of NO2 is 13.4 grams. Find Kp. Right. Now see, the examiner will now mix these questions and has been mixing these questions with moles. I can make you guys do the same question over and over again, or I can make you guys do different types of questions, and I prefer doing different types of questions. The same questions you'll already be doing over and over again, inshallah, when we start doing past paper practice and whatever. But this type of question is now being tested nowadays, being tested in the exam. Nowadays, these type of questions are being tested in exam. So he wants you to calculate the Kp. The first step is to first write the Kp expression for yourself. The first step. So Kp expression equals the partial pressure of NO squared, right, divided by, this is NO2, sorry, the partial pressure of NO2 squared, the partial pressure of NO squared into the partial pressure of O2, right? Now, how do you calculate partial pressure? You ask yourself this. How do you calculate partial pressure? I need partial pressure at equilibrium, right? Now, how do you end up with partial pressure at equilibrium? Sir, I need moles at equilibrium divided by the total moles, don't you? You need moles at equilibrium divided by the total moles, don't you? You do. You absolutely do, right? That's the idea. This is how your thought process should work. Just like when we were doing Kc, it should have been like this, that NO2's concentration at equilibrium, remember NO concentration squared and O2's concentration. This, how should your brain work here? It should work here. This brackets mean I need concentrations at equilibrium. And to, how do you get concentration at equilibrium? I need moles at equilibrium and the volume, right? So this is how it should work. And how do you calculate these moles at equilibrium? How do you calculate the moles at equilibrium if the examiner has not already given it to you? How do you calculate them? So you calculate them through ice tables. So you must be given initial moles. You must be given initial moles. Are you given initial moles? That's the question. Am I given initial moles in this question? Am I? No. Then how do you calculate initial moles? I swear to God, it's a piece of cake. Chapter number 5, moles and stoichiometry. How do you go from mass to moles? Mass equal mole times molar mass. Mass equal mole times molar mass. So how do you go into moles? Moles equal mass divided by molar mass, or you call it MR, which is incorrect, but you still do. I couldn't care less. Moles equals, what's the mass of NO? Let's start finding it. For NO, moles of NO, sir. You're given the mass of NO, which is 10.7. What's the molar mass of NO from the periodic table? 14 plus 16. What do you get, sir? 0.375? 357. Okay. 357 moles. Done. Sir, moles of oxygen. Right? Moles of oxygen. How many moles of oxygen do you have? So you have the mass of oxygen divided by the molar mass. 7.33 divided by oxygen is 16. You have 2 O's, times it by 2. How many moles do you get? 0.299. 229. Okay. Sir, moles of NO2. How do you calculate this? So you're given the mass of NO2 at equilibrium, right here. And this is at equilibrium, by the way. This is not initial. These two are initial, and the other data is at equilibrium. So 13.4 divided by 14 plus 16 times 2. What do you get? 0.291. Okay. I made sure that it looks the same as the previous question. Don't worry. Done. Now it's time. These are my initial modes. Now it's a piece of cake. I just use my ice table. Nothing else. Ice table. To go from initial moles to moles at equilibrium. What's the equation? The equation 2NO, 2 gives me 2NO2. 2NO plus O2 gives me 2NO2. What are the initial moles? You literally figured it out. It's 0.357 for NO, 0.357 for NO, and for oxygen is 0.229. 0.229. Initial moles of products is 0. Right? Now, what are the moles at equilibrium? The moles at equilibrium are given for NO2. It's okay. The moles at equilibrium are given for NO2, 0.291. Right? And if this is 0.291, that means the change is of positive 0.291, and it's positive because products form, they increase, they form, this decrease, that's why there must be negative always here, right? So 0.291, and now you figure out the change here. How? It's 2:1. You use this row to figure out everything else in combination with the balanced equations ratios. So this is plus 2.91, 2:2. This should be minus 2, 0.291, right? Similarly, this is plus 0.291. Half it, what would it give me? The same idea. Minus 0.146. What are the moles at equilibrium? 0.066, 0.083. So it's like the same answer. It is because I made sure the question is similar. So moles, total moles, how many total moles do you have at the end at equilibrium? It's 0.44, same idea. Now calculate partial pressures of NO, partial pressure of O2. Because how do you calculate partial pressures at equilibrium? You need the moles at equilibrium, the total moles at equilibrium. Partial pressures of NO2. If this sticks in your brain, that's it. The basic thought process. So for NO, it's what? 0.066 divided by total moles, which is 0.44, into the pressure, which is what? Which I said was 100 kilopascals. 100 kilopascals. For O2, it's 0.083 divided by 0.44 into 100 kilopascals. For NO2, it's what? 0.291 divided by 0.44 into 100 kilopascals. And what are your partial pressures? For NO, it's 15 kilopascals again. And this is, for O2, it's 18.9 kilopascals. And for NO2, it's 66.1 kilopascals. Okay? Now, figure out the Kp for it. You've already written the expression, just plug it in. You've already written the expression, just plug in these values. So partial pressure of NO2 is 66.1 kilopascals. So 66.1 kilopascals squared divided by partial pressure of NO is what? 15 kilopascals. So 15 squared into partial pressure of O2 is 18.9, and that's it. Done. It's a piece of cake. Sir, thanks. Now it feels a lot easier. I'm glad, Hamza. I'm glad. It's a piece of cake. Done. Next. And the examiner can play around with these equations the same way he used to play around with Kc. And I've done Kc in a lot of detail. Right? Next. What if the examiner does the same thing that he does with Kp? Makes you guys do reverse working. Sir, what do you mean by reverse working? I'll tell you. He says hydrogen gas reacts with iodine gas, gives me HI gas, right? And I'll put a 2 here, maybe a 2 here, sorry, a 2 here. 2 here, oh, it's balanced. I don't have to put any 2s anywhere, it's just balanced, right? Great stuff. Now, the examiner tells you the Kc is equal to 49 and says the total pressure is 100 atmospheres. Nobody gives a shit, right? Find partial pressures. Don't be scared, you guys can do it. Partial pressure of gases. Just one more type of question is left, and then we're done. One more type of question is left, and then we're done with this chapter. Then I just have to teach you guys Lee shortlist principle in the next classes, and we're done. Right? Alright, continuing, guys. Let's do this. So he has not given me jack shit, right? And he's given me the initial. Nothing has been given to me. Nothing is. Oh, let me give you guys the initial stuff. I didn't even write the initial moles. Sorry, my bad. The initial moles are. Nobody even told me. The initial moles of hydrogen are about 0.02, and for I2 are about 0.01. And let me also make it a little interesting. For HI, the initial moles are 0.07. I've made it a little interesting. Now let's do it. Chalo. Sorry guys. My bad. Sorry. Please forgive me. Forgive me. Oh, let me. Please let me live. Live and live. Right? Ice tables. He should be given me initial moles. H2 plus I2 gives me what? gives me 2hi. Let's go. So the initial moles are given, which are what? 0.02, 0.01 and 0.07, right? And the moles at equilibrium, not given. Nothing's given. The change, and this is where things get interesting. What's the change? I don't know. Do I know the change? I don't know. Right? Let's try to figure out our way. Don't worry. All will be well. Don't worry. I don't know the change. It's going to be negative x. I don't know how much this is. And because it's 1:1, if this is negative x, then this should also be negative x, shouldn't it? And this is 1:2. So this should be twice this change. So if this is x change, whatever this change is, this should be twice the change. So can I call it 2x plus 2x? Right? And this is positive because products form. This is negative because reactants are used up. So what are the moles at equilibrium? Frankly speaking, I don't know. It's 0.01 minus x, 0.07 plus 2x, right? All of that good stuff, right? How many total moles do you have? Total moles. Don't worry. Just keep on doing the question. Don't lower your weapons. Just keep on doing it. You know the method. You'll reach somewhere. I promise you would, right? How do you figure out total moles? 0.02 minus x plus 0.01 minus x, right? Plus 0.07 plus 2x. Fun fact, look at this beauty. 2x cuts out with this, and you're left with just figures. What are you left with? 0.02 plus 0.01 plus 0.07. I think that's 0.1 moles. These are the total moles. Let's calculate the partial pressure now. Right? So, and before you do any of that, write the equation. Kc is given to you, and you know Kc equals Kp. So Kc equals Kp. So, and because I'm playing around with pressures, I'll just call it Kp. So Kp equals partial pressure of Hi squared divided by partial pressure of hydrogen into partial pressure of iodine, right? And you're given this. This is 49, right? This is 49 given to me. Now, let's try to calculate the partial pressure of Hi, the partial pressure of I2, and the partial pressure of hydrogen. Let's try to do it. Don't worry. Even if it's in excess, don't worry. Be happy. Here's a little song I wrote. You might want to sing it no for no. Okay, so what's the moles at equilibrium for Hi? It's 0.07 plus 2x divided by the total moles, which are 0.1, multiplied by the total pressure, which is what? 100 atmospheres. Keep on doing it. Don't worry. Don't worry if one is unknown. Don't worry for it. Don't worry. Just keep on doing it. 0.0, how much is hydrogen? 0.02 minus x divided by 0.1 into 100. Similarly here, it's 0.01 minus x, 0.01 minus x divided by 0.1 times 100, right? All of that good stuff. Right. And then just plug it in. I couldn't care less. Plug it in, right? Plug this in right here. So it's what? Do it. Partial pressure of Hi squared. What's the partial pressure of Hi that you've calculated? What's the partial? And I can even ignore these hundreds. I can even ignore this 100. You know why? Because see, this 100 here, this 100 would be multiplied here, right? This 100 would be squared here. 100 squared. And I'll tell you why I'm ignoring it. You can't, if you don't want to ignore it, don't ignore it. This 100 would be squared here, and this 100 would be divided here twice, right? See, 100, and this would be squared here, and this 100 and 100. See, it's raised to the power 1. So they would literally cancel out with each other. If you want to do it like this, you can do it. If you want to multiply it with 100, you can do it with whatever, however you like. I couldn't care less, right? I'm just gonna, remove hundreds because they cancel out with each other. So what am I left with? I'm left with I'm left with what? 0.07. And fun fact, just like the hundreds cancel out, just like that, the 0.1s cancel out as well. Because this is going to be 0.1 squared. This is going to be 0.1 and 0.1. All of this, 0.1 squared, 0.1, 0.1, they would all cancel out. This 100 squared would cancel out with 100 and 100. 0.1 squared would cancel out with 0.1 and 0.1. So you're just effectively left with, if you effectively look at it, if you want to properly solve it, you can. I just want to save time. So you could, effectively, you're just left with this stuff. So the partial pressure right here is 0.027 plus 2x squared divided by 0.02 minus x into 0.01 minus x, right? This is what I'm left with, aren't I? This is what I'm left with. And this is equal to 49. And now I can easily calculate this. Now, again, there are two ways to calculate this. One way is to start doing algebra, take under root like this, take under root like it becomes too lengthy and too difficult. I'm just going to plug it in the calculator, right? I'm just going to plug it in the calculator and figure out x. Don't worry. So guys, this is how you plug it in the calculator, right? What I actually did was, I don't know if you can see it very well, but what I actually did was I wrote 49 and then I pressed the equal to sign. How did I press the equal to sign? I pressed alpha right here, alpha button. And once you press the alpha button, you press calc. Alpha, calc, that gives me the equal sign. So I put the equal sign and then I just used the normal expression. How did I come up with this x? I pressed alpha and this bracket. See, this is the x right here. Right? And then once I'm done putting the entire expression, in the calculator, I hope you all can see it properly. See, I've plugged in the entire expression in the calculator. Now I'm just going to press shift and calc. Shift, calc. See, then it says solve. So shift and calc. See, it's saying solve for x, and I'm just going to press equal to, because yes, I want it to solve for x. And this is how you're going to get the value for x. See, it's 0.0328, right? That's it. So the value that we got was what? The value that we got is, let me put the phone down. The value that I got was what? 0.0358. 0.0358. Chalo, 0.0358, right? These are the moles. I hope this value is correct, right? Okay, so some of you are saying a lot of you are saying, sir, it's 3.03 into 10 to the power minus 3, so we're going to use that value. You can calculate the value on your own now. I've taught you how to do it. 0.003. I'm going to use this. 0.003. Chalo, theek hai. These are the moles, right? These are the moles. Now, what I do is, I wanted to calculate partial pressure, right? This is x equals this stuff. Now, if I just move this a little, right here, I just have to plug this 0.003 right here. Instead of these x's, I just have to plug 0.003, 0.003, 0.003, right? So this would be give me, if I were to plug this in, it's 0.07 plus 2 times 0.003 divided by 0.1 multiplied by 100. This is the partial pressure. 0.02 minus 0.003 divided by 0.1 times it by 100. 0.01 minus 0.003 divided by 0.1 times it by 100. And this is how you end up with partial pressures. Done. This would be partial pressure at equilibrium. Yes. Units nahi hai na. Units nahi hai. So the partial pressure at equilibrium. The partial pressure at equilibrium can be calculated like this. Kitna aasan tha. Acha, fun fact, this type of question is never going to be tested. Do you know why? Because idhar kya hota hai? A quadratic equation forms and you have to solve it through quadratics, and in your exam it specifically states that quadratics are not part of your course. So that's why I just plugged it in the calculator, because I know that quadratics is not part of my course. So after this you could calculate for x, whatever x values you get right here, whatever x value I got, I just plugged it in right here. Right here, x, and that gave me partial pressure. So this is one of the the most technical questions that could have ever been asked, in your exam. Can this be asked? The answer is no. But why did you teach it to us, sir? Because I want you guys to be well versed with every type of question. It's a piece of cake. One last question that I like to do, and then we'll call it a day. Take one last question. Sir, but if we've learned from quadratic method, can we do through it? No, Faryal, because Cambridge assumes, your examiner assumes that if you guys are studying chemistry, you are not studying any other science. If you're studying physics, you're not studying any other science. If you're studying math, you're only studying math. That's the assumption that Cambridge takes. That's why quadratics is not part of your course. Right? It's part of math, but it assumes that not every student is taking math. One last question that I like to do, one last type of questions that I like to do, and then this chapter is almost over. Again, I'll call this reverse working. Right? Reverse working. Question looks like this: PCl5 gas, let's suppose, and that gives me PCl3 gas and Cl2 gas, right? Now the question says that only 69% of PCl5 dissociates when heated. Whatever temperature, when heated at whatever temperature, the total pressure is 2 atmospheres. Right? The total pressure is 2 atmospheres. Find Kp. And this question can be asked. And this is a piece of cake. Again, for Kp, first let's write the expression. Kp equals partial pressure of chlorine into partial pressure of Cl3 divided by partial pressure of Cl5, PCl5, right? Good stuff. Now, once you write this stuff down, I'm not given anything, am I? I'm not given the initial moles. I'm not given anything. Let's try to do something. Let's just use our ice table and I solve questions from your perspective. So if as a student I were given this question, I would stick to my methods. I'm teaching you to stick to your ideas. Ice table, PCl5, because if you want to calculate Kp, you need partial pressures at equilibrium. And how do you calculate partial pressure at equilibrium? Mole at equilibrium divided by total moles. How do you get a moles at equilibrium? You need to calculate it through ice table. So let's do it. Let's try our best to do it. Right? So PCl3 plus Cl2 right here. And initial moles of PCl3 and Cl2 are 0. How many initial moles do you have for PCl5? How many initial moles do I have for PCl5? Do I have any initial moles? I don't know. Even if I do, I don't know. It's okay if you don't know. It's okay. Let's move on. Move on from this. It's okay if I don't know. He's saying that 69% PCl5 dissociates, which means the change is what? The change is of 69%. 69% dissociate means what? 69% is reacting. 69% is breaking down. So can I say if I had X as my initial moles, 69% of X were dissociating. So can I say 0.69 of X it's going to decrease by 0.69 X? Can I not? It's basic math, guys. 69% is the change. And what's the change? It's X. Let's suppose this was, 5. And I say it changes by 69%. So 5 times 69. That's 69%. That's what you would have done, right? 5 times 69%. That's what you would have done. But now I'm saying that the initial moles are X. So what would the change be? It would be 69% of X. And put a negative sign because it's reactive. It's going to be used up. Now again, it's in what ratio are they all in? 1:1:1. So if this decreases by 69%, this would increase by 69%, and this would increase by 69%, wouldn't it? 69% of what? 69% of X. I can absolutely write that. So 0.69X positive, 0.69X positive, right? So what are my moles at equilibrium? 1 X minus this. What do you get? X minus 0.69X. What do you get? 0.31X. What do you get here? 0.69X and 0.69X. Trust me, just keep on doing it. Keep on doing it. Total moles are what? Add all of them together. Add all of them together, sir. Add all of them together. What do you get? Anji? 0.69 plus 0.69 plus 0.31. बोले say it shabash. 0.31 plus 0.61 plus 0.61. 1.53. 1.53 are the total modes, right? Total 1.53x, sorry, my bad. 1.53x. 1.53 are, right? 61 sorry, 69 sorry, my bad. 0.69 plus 0.69 plus 0.31. It's 1.69x. Sorry, my bad. It's 1.69x. It's 0.69 plus 0.31. Now let's calculate the partial pressures. Don't worry. Let's try to do it. Partial pressure of PCl5, partial pressure of PCl3, and partial pressure of Cl2. What do you get, sir? Partial pressure equals the moles at equilibrium divided by the total moles into the total pressure which I have given to you. It's 2 atmospheres. So let's do it. Sir, the moles at equilibrium 0.31x divided by the total moles 1.69x into the pressure, which is 2. Total pressure, right? Similarly here 0.69x divided by the total moles 1.69x into 2. 0.69x divided by 1.69x into 2. And what do you see? Voila! What do you see? X and X cuts out. X and X cuts out. X and X cuts out. That's why I tell you to just keep on going. Keep on going. Keep on going. Right? So, what's the partial pressure of PCl5? Right? And 0.367. What's this? 0.817. What's this? 0.817. Now let's calculate Kp. Kp is equal to partial pressure of PCl3 plus partial pressure of Cl2 divided by partial pressure of PCl5, and they're all raised to the power 1, 1, 1, 1, 1. So Kp equals 0.817 squared, 0.817 divided by multiplied by 0.817 divided by 0.367. What do we get, sir? What's the unit? Unit is ATM. Right? Because unit ATM squared divided by ATM. ATM cuts out with ATM squared, right? So you get ATM left. Whatever you get, that's the answer. Finished. I've done 2 of the most difficult questions that could ever be asked in your exam. Can this question be asked? Absolutely. This question can definitely, most definitely come in your exams, especially in MCQs, right? Can this type of question be asked? The answer is no. But it's good that you know. It's good that you know, right? It's just quadratics. The reason is quadratics that it can't come in your exam. And then this is the basic question. So it's the same idea that you used with KC. Right? Only one new thing that we studied right here. Beautiful, isn't it? Beautiful.